In this video, we look at what's called an instrumentation amplifier, and an instrumentation amplifier is a differential or difference amplifier modified at the input. So this dash box here with the DA, that stands for difference amplifier. That's the same circuit that we went over in a previous video. And what we're doing here is in between the inputs V1 and V2, we're putting this op-amp circuit. So now we're taking the output of these two op-amps and feeding it to the input of this difference amplifier. So if we take the difference amplifier equation that we came up earlier and replace V2 with VO2 and V1 with VO1, we have the expression for Vout. So what we're going to do in this analysis to see what effect this circuitry has on our output over here is first we're going to define a current flowing from V02 to V01 that I'll just label I. And remember that we have a virtual short at the input of these op amps. So this current here is 0. The voltage across the inputs here is 0. Okay, likewise, same thing down here, voltage across this input 0. And this current here also 0. So because ideally no current is drawn at the input of the op amp, all this current that I defined as I is flowing just in this single path. So VO2 minus VO1 would just equal that current I times the total resistance in the path, which we've got 3 resistors in series, so it would just be 2R3 plus R4. Okay, and now we can write I in terms of V1 and V2, because see here this node that I labeled VA, well that's going to be the same voltage as V1. Okay, VA equals V1. Since the voltage across the input of the op amp is ideally 0, that means voltage is the same on both inputs like we've seen many times. So you see VA is equal to V1 and VB is equal to V2. So those voltages are connected right across this resistor R4, so I can write I also as V2 minus V1 over R4. Okay, and then I just plug this up here. So then we get that VO2 minus VO1 is just V2 minus V1 over R4. And then that's going to be times 2R3 plus R4. Alright, so we can simplify this. Okay, and write that now Vout, well actually, in addition to simplifying, what we're going to do is take this expression for Vout2 minus Vout1 and put it up here into our differential amplifier equation. So we get this additional factor of R2 over R1. Okay, so Vout, after we make that substitution, and we also just multiply through by the RF, or excuse me, we multiply through by, let's back up just a second. So we're going to plug this up into here, and then just bring the R4 inside over here. Okay, so just bring the R4, so we'll have 2R3 over R4 plus 1. Okay, so let me write that all out. That VO2 we can write as R2 over R1, and then that's going to be times 1 plus 2R3 over R4, and then that's going to be times the difference of V2 minus V1. Okay, so this is our expression for V out, and this is how it gets modified by that op-amp circuitry in front of the differential amplifier. It's this term right here, because R2 over R1 times the difference of the two input voltages, that's the same as a differential or difference amplifier equation at V out. But you see the op-amp circuitry in between where the inputs are, where the differential amplifier is, well, it produces this factor here, this 1 plus 2R3 over R4. And if you go back and look at the circuit again, you can see that these two op-amps over here are very similar to non-inverting amplifier op-amps. You know, if we just looked at this top op-amp here, and if R4 was grounded on this side, it would be a non-inverting amplifier. Or if we just look at the bottom op-amp circuit and R4 was grounded at this side of R4, this would be a non-inverting amplifier circuit. But you see R4 is kind of shared between these two. So that's why it's not exactly you know, two non-inverting amplifier circuits, because the two circuits are sharing this R4, but it's similar, and the expression we get is similar to the expression we would get for a non-inverting amplifier. It's just that we got a 2R3 here instead of just a single resistance like what you saw with the non-inverting amplifier. Now, often with these types of op-amp circuits, the instrumentation amplifiers, often the resistance values are made equal, so R2 is made equal to R1 is made equal to R2, which is made equal to R3, okay, which is some R. Okay, and then also R4 a lot of times is a variable resistor that's labeled R gain. Okay, so often it's you know, a variable resistance like a rheostat. Okay, so a lot of times in practice you'll see this expression written the following. Okay, so if we just make these substitutions into this equation here, it reduces to this. So the R gain, by making that a variable resistor, you can vary the gain for your output voltage. A lot of times this type of op-amp will come in a single IC package that, you know, the differential amplifier circuitry along with all this circuitry is all integrated into a single chip that's called an instrumentation amplifier chip. And there'll be connections, pins on the chip to connect to a variable resistance on, say, a printed circuit board, and the user has the ability to change this resistance. Okay, it's a variable resistance shown by an arrow in a circuit diagram like this, and that just gives some flexibility as far as the gain for a particular, you know, for whatever a particular application calls for. Now, the reason instrumentation amplifiers are very common, in fact, you know, probably more common than just a difference amplifier, is because instrumentation amplifiers have very high CMRR. So remember, we talked about this last video, that the common mode rejection ratio is a measure of how well your amplifier is amplifying the desired signal compared to amplifying the noise signal, which is undesirable. So by putting this couple of op-amp amplifiers that are sort of like non-inverting amplifiers before the difference amplifier, you actually improve your common mode rejection ratio. That, you know, these op-amps here are amplifying the signals themselves, V1 and V2, before the difference amplifier amplifies the difference of the two signals. So this is sort of like pre-amplification before the main amplification takes place. And when you do preamplification, it improves your CMRR, which really is another way of saying that you're improving your signal to noise ratio, if you've ever heard that term.